Now that we've had that exam, we'll move into a new area, one that usually makes students feel a lot better about themselves, because we're studying little thermodynamics things. We're going to start working with things like the ideal gas law today. And most students, be it in high school or college, physics or chemistry, high school physics, obviously for you, college or high school chemistry, you've already covered this. So hopefully there's going to be a lot more comfort as we go through this, simply because a lot of students already know this and I'm just reviewing. So let's get started. I'm sorry, I take slides from many different classes, and this one here had the ever-hated Comic Sans or whatever it's called font. But the ideas of temperature and heat are ones that we often get very confused. And so one of the things we're going to learn in the next week or two is the difference between temperature and heat. And today I'm going to focus on temperature, but you really have to identify what both of them are just so you can have a contrast to differentiate. So temperature, we all know, it's hot, it's cold. If I touch this hot plate, it'll burn me because it's hot, right? Well, when it burns me because heat flows into me. Heat is energy moving. Now, we've already learned about one energy transfer name. What's the name that we've learned for a transfer of energy? Work. Work is a transfer of energy. Heat is also a transfer of energy. What's the difference in the two then? Work involves a force and motion parallel to that force. Heat only involves a transfer of energy without that motion aspect. So there's no force or motion aspect when you talk about heat. It's just a transfer of energy. And so this example here of the drill press is actually almost exactly what led to the first understanding of heat. Back long ago, before I was born, of course, people believed in what they called the caloric. In fact, their theory had the caloric and the frigidic. And the caloric was a fluid that would bring heat. And the frigidic was a fluid that would remove heat. And they believed that there must be this caloric and frigidic flowing through things if they were getting hotter or getting colder. They didn't know what it was. They did experiments and couldn't find what it was. And then the actual observation that led to a better understanding was, and I can't remember the name of the gentleman, but he is very famous. He was drilling cannons, and he observed that, it developed a lot of heat when he was drilling. And so he made the connection that the work he was doing on drilling was making the temperature higher, and so that then there must be a relationship between the work and the heat. And then, we have Joule's experiment that gave us an actual relationship for that. And so the idea of the frigidic and the caloric has now been completely abandoned. We don't believe there's a fluid magically going through material that makes it heat up or cool down. It's just a transfer of energy. But that's a little history on that. So how do we measure temperature? When you are home sick in bed like this gentleman, how does your mom or dad measure your temperature? They take a thermometer, you stick it under your tongue, right? Sublingual. What is the thermometer actually measuring the temperature of? It's actually measuring the temperature of itself. You put it under your tongue and the thermometer warms up. Heat naturally flows, and this is actually a statement of the second law of thermodynamics. Heat naturally flows from something that's a higher temperature to something that's a lower temperature. And so if you put that thermometer under your tongue, if your body is hotter than the thermometer, which it generally is, then you should have heat that flows from your body into the thermometer. The thermometer will get hotter until, given enough time, the thermometer reaches the temperature of your body. That's why you can't just stick it in, take it out, and say, my body temperature must be 72 degrees Fahrenheit. right? You got to stick it in there and leave it for a while. So we're measuring the temperature of the thermometer and letting it reach what we call thermal equilibrium. So lots of words here to learn, but they're very simple ideas. Thermal contact. Thermal contact means that I have the ability for heat to pass between two things. So for instance, if I touch this hot plate, I will indeed make thermal contact with it. Heat will flow into my finger and it will burn. If I don't touch it but I come near, I'm still in a kind of thermal contact because my finger is getting warmed up, just not nearly as much as if I was touching. And we'll learn about 3 different forms of heat: conduction, convection, and radiation. In that case, it was mostly convection. If I hold it over here, it's going to be mostly radiation. But thermal contact means you have them so heat can be exchanged. And one of the fundamental laws of thermodynamics, so fundamental nobody thought you would ever have to make it a law, is that if object A is in, I've already said this, but I want to make sure it's clear. If I bring 2 things in thermal contact, what do I say about the flow of heat? It goes from hotter to colder. So if I have one thing that starts at, let's say, 30 degrees Celsius, another one starts at 10 degrees Celsius, is the one that starts at 30 degrees Celsius ever going to be colder than the one that starts at 10 degrees Celsius? No, because when they get down to the same temperature, you just have no more heat flow because it goes from hotter to colder, but neither one's colder. So we say that you're in thermal equilibrium when they reach the same temperature. So thermal equilibrium is exactly the same as saying the same temperature. So the 0th law of thermodynamics says, if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object C. Now, based on what I just said, writing that mathematically, that's saying if temperature A equals temperature B, because that's what it means for them to be in thermal equilibrium, and temperature B equals temperature C, those two are in thermal equilibrium, then the truly preposterous temperature A equals temperature C. Does that seem obvious? Mm-hmm. Seemed obvious to physicists too. No one ever thought that they would have to make that a law. But as they started understanding what temperature really is measuring, and understanding that temperature is a measurement telling us about the average kinetic energy of molecules, it suddenly didn't become so obvious. And so they decided they're going to have to make this a law because it wasn't obvious when they actually understood what temperature was measuring. But they'd already made a couple laws. And they said this is more fundamental, so they call it the 0th law. So it's more fundamental than the first law. So the 0th law of thermodynamics, if object A is in thermal equilibrium with object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object C. Or, as I wrote down here, the mathematical equation. Seems real obvious. It's just something we have to go over because when you understand what temperature is, which in this class we won't get so sophisticated that it'll seem jaw-dropping, it becomes necessary to actually state that. So here is an example. I guess that's sweat on my screen. An example of what happens when I bring 2 things into thermal contact. I have here 2 blocks. Doesn't matter which one's bigger, which one's smaller. It matters which one's hotter and which one's colder as to the direction the heat will flow. So as long as temperature 1 is greater than temperature 2, it's going to go from the big one to the small one. If temperature 2 is greater, heat would flow the other direction. So I can have a little tiny thing like a BB that's super hot, like let's say, 200 degrees Celsius. And if I put that little BB in a big container of water that's 20 degrees Celsius, the heat's going to flow out of the BB into the water because it always goes from the hot to the cold. It doesn't matter which one has more total energy. It's about the average energy, the temperature. Temperature scales. In 1724, Gabriele Fahrenheit came up with a temperature scale that is not widely used anywhere except for here in the United States. So there are different stories on how he came up with this, but what he wanted to do was to have some way of actually gauging and comparing temperatures. And so he noticed that you have a fluid, and the fluid will expand when it gets hotter and contract when it gets colder. We're going to look at that in just a little bit. And so using that, actually, it might have been a gas. I don't remember his method. So he chose 2 calibration points. And I am sure nobody knows exactly what those calibration points were, because I have like 3 different textbooks that give me 3 different answers. But what has generally been laid out is he chose 0 degrees to be the temperature of ice/seawater. Not the temperature of pure water and ice, but seawater and ice. And then he took 100 degrees Fahrenheit to be the basal body temperature. And I have seen of a bovine or of his wife. I don't know which. These were his calibration points. It goes from 0 to 100. If it goes from 0 to 100, we call it a centigrade scale. Centi meaning 100. So it has 100 steps between the 2 calibration points. Now, would you consider this a good or a bad calibration? Bad. Why would it be a bad calibration? Yeah, subject to change. If you change the salinity of that seawater, you're going to change the freezing temperature of the seawater and thus change the 0 degrees Celsius definition. And of course, you get sick, you get up in the morning, you have different temperature, and you get up in the morning and you do, after working out, body temperature changes. So those are pretty bad calibration points. So then, 1742, that's what, 18 years later? Great Swede. Now, I am a quarter German and a quarter Swedish, so I guess that, or is it quarter? No, I'm an eighth Swedish and an eighth German, whatever. Doesn't matter, does it? I'm half Scandinavian. We're going to Scandinavia this summer. That's what matters. I have relatives that have a ski resort in the city of Ski, so we're going to go visit that. Anders Celsius said, let's make something that's a more reproducible calibration system. And so Anders Celsius said, I'm going to take for my reference points 0 degrees Celsius equals the temperature of boiling water.
Freezing water.
And 100 degrees Celsius is equal to the temperature of freezing water. I did not make a mistake. I know you all think I did. So that was his scale. Is that a centigrade scale?
Yeah.
Yes. But of course, the temperature for boiling and freezing water is a much bigger difference than the temperature from the freezing seawater to body temperature. So that means that a degree in the Celsius scale actually represents a bigger change in temperature than a degree in Fahrenheit. Now, everybody objected right away when I said 0 degrees Celsius for boiling water. But that's what Anders chose. But Anders died just a couple years later. And then people said, let's turn it over and make it so it makes more sense. Why does it make more sense? Because we now understand that temperature is a measurement proportional to the average kinetic energy of molecules. Well, what's the maximum kinetic energy a molecule can have? There's no limit, right? What about the minimum kinetic energy? 0. If you have a kinetic energy of 0, that's the minimum. You can't go into a negative kinetic energy. You can't, 1/2 mv squared can't be a negative value. And so that means that there's an absolute 0, a lowest possible temperature. Now, quantum mechanics says that at absolute 0, the kinetic energy is not 0. It's not possible to get to 0 kinetic energy, but the lowest possible kinetic energy stays where you get absolute 0. So that's why they turned it over, so you would go down in number when you're going toward the minimum, and then you'd go open-ended as the going up side. Now, so I'm going to now just change the numbers here to match what it is currently. So there's the current reference points. Almost. back when I was a young buck, like, I don't know, I think it was around 1976. So I was like in 3rd or 4th grade. They changed the definition of the Celsius scale. They changed it so it's no longer a centigrade scale. It now has for its reference point a number that's between these. Let's see, there's a way for me to move them and put something in between. Except for I missed the ing. There, perfect. No. 0.16 degrees Celsius is the triple point of water. That is, there is only one combination of temperature and pressure where you can have the 3 common phases of water, ice, liquid water, and steam, all coexist. And so that's the reference point for the low side of the Celsius scale now. So it's actually 0.16 degrees off of being a centigrade scale. So you don't have to worry. When I was a kid, sometimes they say centigrade and sometimes they say Celsius, and I was really baffled. But then, now they're different things and nobody ever uses the centigrade. We always use Celsius. So just, the difference there. I know it doesn't matter to you. Yeah, probably not. Okay, looking back at the thermometer that has Celsius and Fahrenheit, these days, all of our temperature scales are made on the same calibration. So it's just putting different numbers to the same calibration. And so because of that, just putting different numbers to the same calibration, the conversions have been made exact. So that 0 degrees Celsius is exactly 32 degrees Fahrenheit. And 100 degrees Celsius is exactly 212 degrees Fahrenheit. So if you know Fahrenheit, you know Celsius, they're using the same calibration, so there's no funny business going on. Notice that the difference between 212 and 32 is 180. And the difference between 100 and 0 is, not surprisingly, 100. So that tells you that a change of 1 degree Fahrenheit is the same as a change of 5/9, that would be 100 divided by 180, degrees Celsius. Or a change in 1 degree Celsius is a change in 1.8 degrees Fahrenheit. And so for making our conversion between Fahrenheit and Celsius, we start with this ratio of 5/9, which is just 100 over 180. And then we have to take the offset between 0 to 32. So temperature Celsius is temperature Fahrenheit minus the offset of 32, and then times that ratio of 5/9. Or, of course, you can solve the other way. Temperature Fahrenheit is 9/5 temperature Celsius plus the offset 32 degrees. If you take these equations, you can calculate at what temperature is Celsius and Fahrenheit the same. It's actually a question that's in the test database. Well, all you have to do is say, let's just call this T equals 9/5 T plus 32. Right? If they're the same, I can just use one variable. And then solve that for T. So move the 32 across and the T across. Minus 32 is equal to 9/5 T minus T. 9/5 minus 1 is, of course, 4/5. (32 divided by 4 is 8. 8 times 5 is 40. So minus 40 degrees Celsius is the same as minus 40 degrees Fahrenheit. Now, I'm a physicist. We physicists think that we are the funniest people alive. And we love to tell jokes like, man, it is so cold out, it's minus 40. Is that in Fahrenheit or Celsius? And then we slap our thighs and laugh like crazy little hyenas because we think it's so funny. Don't you wish you could be in our little group? You got a great sense of humor. I mean, you guys know the quarks, right? We don't have any of the stuff in this classroom, but the quarks, the first two, they said, well, let's just call them up and down because they thought there were just 2 flavors. But then they discovered that there had to be, there's a strange behavior. And so they said there must be another one. We'll call it strange because it causes the strange behavior. But their theory said that you had to have a fourth. And they said, oh no, we can't find the fourth one. It must lead to charmed life. So they called it charm. So your first four quarks are up, down, strange, and charm. And then their theory said there had to be two more. And they said, well, let's give them names of top and bottom. And the good physicists said, top and bottom? That is boring as sin. We're going to call them truth and beauty. Because we've got that kind of humor going on. Okay. Absolute zero. I'll talk about why absolute zero occurs in just a few slides, but there is an absolute zero, a minimum temperature possible. And in the Celsius scale, absolute zero is minus 273.15 Celsius. On the Fahrenheit scale, just using that conversion equation, that comes out to be minus 459.67 degrees Fahrenheit. So either one of those is absolute zero. In science, we do not use the Fahrenheit scale, right? I use that all the time for things like, man, it is hot out. It's, 80 degrees. I often don't say Fahrenheit, which slays me because, units are important. 80 degrees could be, well, we're going to not survive if it's 80 degrees Celsius because that's too hot. Or we're not going to survive if it's 80 degrees Kelvin because that's too cold. So what's the Kelvin? Well, first of all, you do not say degrees and Kelvin together. So 80 degrees actually can't be 80 kelvins because you don't say 80 degrees Kelvin. So you notice there's a degree sign for Fahrenheit, for Celsius, but not for Kelvin. So the Kelvin scale is an absolute temperature scale. What that means is they just said, let's take the Celsius scale and offset it by this 273.15. So you just say, well, temperature in Kelvin is equal to temperature in Celsius plus 273.15. That's the only difference. And I know most people here probably are very aware of this already. But that's how you define our absolute temperature scale that we use in physics. Now, in most situations, it doesn't matter if you use Celsius scale or Kelvin scale. But some situations you have to use the Kelvin scale. Why would it not matter? Because these are linearly proportional to each other. A change of 1 degree Celsius is the same as a change of 1 Kelvin. And so if you're just looking at a difference in temperature, it doesn't matter if you're looking at kelvins or Celsius degrees. On the other hand, if it just says the temperature, something is proportional to the temperature, you have to use an absolute temperature, so you have to use Kelvin. So pretty much almost never will you be wrong if you use Kelvin. But if it's a change in temperature, you can use Celsius. Now, what if we were old school? What if we wanted to use Gabriel Fahrenheit's temperature scale? There is a temperature scale that you are not responsible to know a thing about that's called the Rankine temperature scale. And temperature Rankine is equal to temperature Fahrenheit plus 59.65?
Yes. 467.
459.67. I was really close. So that's the Rankine scale. It's also an absolute temperature scale, but we simply won't use it. If you ever see it, you can know what it is. You will not see it in my class on any kind of test or homework, I don't think. So everybody down with the temperature scales? Good. Let's do things that are more fun. First, we'll ask a question. Which statements are true about the Celsius temperature scale? Can you connect to there, Gabriel?
Yeah.
It it still doesn't have an answer. Don't have yours. Okay, let's move on. We have some pretty tight numbers here. 32, 31, 34, 15, and 24. Now, there are only 2 correct answers here. So discuss with the people around you, and then we'll poll it again. See if you can determine which 2 are the correct answers. Oh, crap. It tells you which ones are correct. I was not. This whole discussion thing is ruined when it tells you which one's correct.
No, not in the clickers.
Yes, not in the clickers. Well, going to have to rethink this showing the...
Discuss.
Well, I can actually just make it so it doesn't show what the correct answer is. I had not seen that before. Okay, let's go ahead and re-poll this and see if you could all match what your clickers told you. I learned things. Look at that. Pretty uniform now.
Doing a new thing. You can go help out.
Okay. Hey, we got a lot more people answering this time too.
Yes, it is. I don't like it.
Do you not have a clicker, Joel? No. All right. So this time we had 53 and 50, 2 people here and 4 people here. And yes, under Celsius was a Swede. And originally 0 degrees was the temperature of boiling water, but it was flipped over. It was originally a centigrade scale, but it no longer is because now it's going from the triple point to the boiling points of water, which is slightly less than 100 degrees. And it's not an absolute temperature scale. The absolute temperature scale, actually, no, the one somebody answered there was, it's the SI unit of temperature. The SI unit of temperature is kelvins. All right, measuring temperature. We already talked about sticking that thing under your tongue and you have a fluid in the thermometer. Back in the day, it was mercury. But people decided that it wasn't healthy to have mercury in your mouth just in case you're a stupid person. Okay, I've never done this, but I've always been really scared of actually snapping that thing in my mouth. You know, I mean, I've done stupid things. I've accidentally broken a mug holding it in my hand apparently wrong. I have a gash on my wrist from washing dishes too hard. So this is not an unfounded fear. But they decided that it wasn't very healthy to have that mercury. Now, I'm old school, right? When I was a kid, somebody brought a bottle of mercury to school. We played with it on the bus. It fell on the floor. We tried to all get down our hands and knees and collect it up from the floor of the bus, get it back in that container. Didn't make us crazy, right? Come on, a little affirmation here. No, but, you know, the fear is you get heavy metal poisoning from it. And, you know, like Mad as a Hatter, at least from what I've read, that's because they used mercury in their felt. And so they were constantly creating mercury vapor and the aroma and build up enough of that and it causes problems. So now they put alcohol in there, not, you know, ethanol. Don't go breaking these things and trying to get that little ounce of fluid to. True story, when I was in high school, a company gave us, MBA, Monterey Bay Academy, a huge case full of 20% alcohol mouthwash. And the school was like, well, we're not giving this to the students. And so they kept it in the maintenance building. So the maintenance workers would take them in. I don't know how you can drink mouthwash, but yeah. Yeah, 20%, it doesn't take that much to get, you know, polluted a little. Okay, the second one here I'm actually going to demonstrate in just a moment. It's called a bimetallic, forgot the last word, strip. A bimetallic strip, you take two pieces of dissimilar metals and you bond them together so they can't slip against each other. And then when you heat them up, when things heat up, they expand. We call it linear expansion or thermal expansion, excuse me. And so one of them expands more than the other. And so they actually form a circle, because if you have a circle, the inside of the circle, that's not the blue color I just selected, still not blue, there we go. The inner side of the circle has a smaller circumference than the outer side of the circle. And so the circumference is going to depend on how much the temperature changed and how much each one expands with the change in temperature. And so by measuring how much it's curved, you can determine what the temperature is. This third one I have shown, anybody ever used one of those things? They'll like put it on your forehead. And you have temperature reactive polymers that change color at different temperatures. And so you put that on and, it just changes temperature up to, the color that matches your temperature. And so you can get the temperature. That's also how, at least we used to be able to buy batteries with a little battery tester. And what that tester had was just a resistor underneath with a temperature sensitive polymer on top of the resistor. And you touch that to both sides of the battery, current goes through the resistor, it gets hot. Depending on how hot it gets, you have more or less of the polymer change color. That tells you if it's good or bad. This last one is the coolest one. The last one is a no contact method. I know in biology, you may have used some of my thermometers that don't require contact. It's looking at the radiation that comes off of an object, and the radiation has shorter wavelength for its peak when something's hotter. We'll learn about Wien's law later. And so that's a way to measure temperature without having any contact. Very cool. So let's look at this thermal expansion. You guys have seen, I'm sure, things like this on bridges. The purpose of that is because as the air temperature changes, it's going to expand or contract. And what you really don't like to have is your bridge to do things like break apart or buckle. And so they put this expansion joint so it can slide and stay flat as it gets longer and shorter. In normal highways, like you drive down I-80, you have little cracks in those concrete slabs. Those cracks have the same purpose, to allow the concrete to pull apart or push together as temperature changes. So they actually serve an important function. They don't just annoy you because it goes click, thump, 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 thump as you're driving down the road and you think you have a flat tire. That's not the purpose. I have two equations on here. One is the change in length for an object is equal to its original length, L0, multiplied by a parameter alpha that depends on what the material is, and then the change in temperature. What unit should I use for that change in temperature? Kelvin or Celsius. If it's a change, I can use either one. It's going to be the same answer. Change in volume, essentially the same equation except for you replace alpha with beta. And beta is approximately equal to 3 alpha. It's actually easy to work out why that's the case. If you just say, well, I have a cube that is length L on each side, then the volume is equal to L cubed, right? And so that means the change in volume, well, when you heat it up, you have volume plus delta V, that's your new volume, is going to be equal to the new length on a side, cubed. And then you put in the equation for delta L. I should have put sub-zeros here. I have that on the right-hand side. Well, if I multiply that through, you've probably learned, was it Pascal's triangle, where you have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So that you can do this real quickly. Okay, there's going to be L naught cubed in each one of these. I'm just going to put cube there. Multiplying that through, since alpha turns out to be a really small number, alpha squared is really, really small. And so we say alpha squared and alpha cubed, those are negligible in size. Wrong button. Fortunately, there's an undo button. Those are negligible in size, so those terms are approximately 0. And so I have V naught plus delta V is equal to L naught cubed plus 3 L naught cubed alpha delta T. But since V naught is L naught cubed, I can subtract those out. And I have delta V is 3 L naught cubed, which is V naught alpha delta T, capital T. And so those together make beta 3 alpha. So it's really easy to see how that comes about. So here is a listing of those parameters, but let's go and do our first fun thing. Piece of metal. Try to get it as straight as I can. Put it in the flame. And what's happening? Man, what's happening? Okay, it's clearly curling. Why is it curling? It's two types of metal, and one type is expanding more than the other as I heat it up. And so obviously I have it preheated up. It was so hot that it was giving off red light. That's part of how using the non-touching thing works. When you get it hotter, it gives off shorter and shorter wavelengths for its peak, and it's much, much brighter. So that's an example of thermal expansion. You can see how you can use this for a temperature gauge. You just put two pieces of different metal together. As the temperature changes, the curvature changes a little. So you probably have seen, I'm going to come right back to this, but turn off just so I don't waste Dr. Clark's personal gas there. You've probably seen like a garden thermometer that has something like that inside. The entire spiral is a bimetallic strip. And so you're having that entire thing having a very slight adjustment as the temperature changes, right, going to either smaller or bigger circumference, and thus moving this needle. So behind here you have your temperatures, 70, that's a 7, trust me, 60, and so on. So that's how those things work. Now, I should have asked this question before, but I'll do it here. I have a brass ball and a brass ring. The ball fits through the ring. Bueno. Now, I'm going to heat up the ball. What will happen to the ball as it heats up? I tested this before class, and I had to wait 30 seconds. So it takes a while for this ball to heat up. And, of course, it was dry when I did that, so probably a little more than 30 seconds. But if I heat it up enough, it expands and doesn't fit through. Well, there, it's just barely fit through. So let's heat up a little more. Get it so I can't get it through at all. Okay, won't go through. Now I'm going to heat the ring up with it. And this only took about 10 seconds to heat up the ring, unfortunately. As I heat them up together, the ring, what should the ring be doing? Expanding. There we go. Now I can, gotta keep it hot. There we go. Now I can fit it back through. This is also cool. What was happening when I stuck those in the water?
They were giving off so much heat that they were creating a barrier.
Okay, they were much, much hotter than the water. And so, as Rachel said, the heat going into water was going in so rapidly that the water was very quickly boiling where it made contact. And so that's what made the sound there, was the rapid boiling of the water making contact. And we call that quenching. So when you're talking about thermal expansion, if I want to calculate the radius of a hole, I would use exactly the same equation. How do you calculate the radius for the expansion of this? What equation would you use for calculating how much the radius expanded as I heated it? I would use delta L is equal to L naught alpha delta T, right? Because radius is a length. And so if I want to do the same thing for the hole in this, I just treat it like the hole is made out of the material that the ring is. And if you want to convince yourself why the hole has to grow, right, you tend to think, oh, this should get thicker so the hole gets smaller. But the hole has to grow because if this was solid, of course, this ring would be around a solid piece and it would have to grow to give room for the solid piece. So you can treat a hole like it's solid material in terms of the expansion. Okay, so a problem, yeah, we can go through the problem and do a little more. It's very interesting. The textbook has a couple things about your gas tank. And here's an example from the textbook about, well, we're not running out of gas here. Here we're losing gas. It had two problems, one about running out and one losing. So suppose you have a 60-liter tank that's made out of steel. And you fill the tank up when it's 15 degrees Celsius. But then it's a hot day and it gets up to 35 degrees Celsius. What's going to happen as the temperature increases? So let's break it down in two pieces. What's going to happen to the size of the tank as the temperature increases? It's going to increase. So I'm going to have an equation that says the volume for the tank is equal to the volume initial times beta for the tank, delta T. What about the volume for the gasoline? Same equation, same initial volume because it was completely filled, but this is going to be the beta for the gas times delta T. Now, which one expands more? Offhand, you're not going to know unless you've already looked this up, I'm guessing. But we have the table here, and petrol is gas. So beta for the gas is 950. The units are just per degree Celsius, right? It doesn't have units of volume or anything. It's just per degree Celsius because the equation has the volume out front times beta times change in temperature. It's a steel tank. The steel is here, 35. Notice when we look at these numbers, 25 to 75, that's 3 times. I'm only going to look at easy ones. So 9 to 27, that's 3 times. 3 to 9, that's 3 times. 2.5 to 7.5, 3 times. That rule of about 3 times is really a good rule. So I can look at this and I can say the gas expands more, which means I'm going to have gas that overflows. Either that or I burst the tank. And so if the tank is sealed so it can't leak, the tank will actually burst. That's bad. So it needs to be able to leak a little. And then we just say the volume leaked is equal to the volume of gas minus the volume of the tank, which would be the initial volume times delta T times beta for the gas minus beta for the tank. I factored out the two things that were the same change in temperature going from 15 to 35, same initial volume, and then I just put in my numbers, 60.0 liters times 20.0 degrees Celsius times 950 per Celsius degree minus 35 per Celsius degree. And so 915 times 20 times 60. What is it?
I get like 1,998,000.
I made a mistake. That mistake was a simple mistake that won't change your number. I forgot there's times 10 to the minus 6 there. Remember I said the alpha is a really small value? So you just divide it by a million. Because, yeah, that's an unacceptably large number.
So 1.098.
1.098. That's actually a lot of gas to lose. I'm trusting your math here. That's a lot of gas to lose. That's going to be, roughly 2 liters to a gallon. So that's, like losing half a gallon. It's at least $1 of lost money, which to me is huge. I don't know. You guys may be fine with that. The book also points out when the gas gauge says 0, it means you have a certain volume. But when it's cold, that volume contains a lot more molecules of gasoline than when it's hot, which means that when your gas gauge says it's empty and it's cold, you've got a lot more miles you can drive than when it's hot and the gas gauge says it's empty. So you actually need to keep temperature in mind. Don't just say, oh, I can always go 50 miles after it says empty. Depends on the temperature how much you'll be able to go. Now, this is really, really important to life on Earth. Water is not normal. If water was normal, we wouldn't be here. What's abnormal about water? Water, if you cool it down, it contracts until you get to roughly 4 degrees Celsius. At 4 degrees Celsius, if you cool it down anymore, it starts expanding again. That's not normal. And then when it freezes, it expands a lot. So this here is the freezing change. That has a downside. That has the effect that if I forget to, drain my sprinklers in the yard, when we have our nice, good, cold, snowy day, I will have the hoses burst because the water inside will expand when it freezes and there's not enough room in the hose to hold it and breaks it. So that's what that picture at the very beginning was, a pipe had burst because water expanded. So we have a downside, but we have a really big plus side because ice floats. And here's why that's a plus. When it's cold, we form ice on lakes. If you go up to Minnesota, you'll find lots of ice covering lakes, I'm told. Never been up there in the wintertime. Well, I have. Watched the Raider game, of course. But I didn't go out to any lakes. We lost. Sad. So you form this ice. If ice was more dense than water, which is what happens with almost every material, what would happen to that ice? It'd sink to the bottom. And so then we'd have some cold ice at the bottom, and the water on top of the lake would freeze and sink and freeze and sink. And so we would start icing the lake from the bottom up. And the lakes would actually freeze solid, which would, first of all, allow us to put a lot of, to remove a lot of heat from the water that right now is being kept in. Water or ice is actually a pretty good insulator. And so the ice allows you to have water underneath that's warm enough for the fish and whatnot to swim around and be happy. And sunlight that comes on top gets reflected off of the light. We say it has a high albedo or high reflectivity. And so the earth absorbs less sunlight because of that, but we also keep our heat in. And if we didn't have ice sinking, then the lakes would freeze through, and then in the summertime, they would probably remain partially frozen. And of course, you wouldn't have, most of our fish would die, right? And it would get colder. It would be bad for us. Just like we have to have the greenhouse effect or it would be too cold, we also need to have ice doing this, actually getting less dense when it freezes, or it'd be actually too cold for us. So that's an important thing. Hey, look, quicker question number 3. What would happen to a lake in the winter if ice was more dense than water? Okay, I only got 20 seconds left, so I'm going to stop it here. We had 9 that said they would never freeze over and 40 that said they would freeze solid. The 40 were correct. Because I have my water all set up here, I'm going to do this demonstration as we leave. Water that's hot. I have a bulb here that is just trapping in molecules, so it's going to keep the same number of molecules. Pressure gauge. When I put this in, what's going to happen to the pressure? You can see indeed the pressure goes up. This is an important law that apparently we're not going to talk about until Friday, but we're going to talk about gas laws and ideal gases next, and seeing how that works. Now I'm going to release the air pressure and take it out. If I take it out now, the air pressure, when it cools off, is going to better be dropping.
It's slowly, but yes.
Okay. This one here has too much water for me to jam it down in. Okay. Have a good day, and I will see you again on Friday.